Welcome back. Last time, we looked at the benefits of developing your next application using Maxim's microcontrollers and nexpaq smartphone integration and developing your firmware on ARM's Embed platform. We saw how, by writing some relatively simple C++ and HTML code, you could control smart modules that plug into nexpaq's phone cases and battery packs directly from a simple iPhone or Android app. Today, we'll get everything set up so that you can begin developing exciting applications on this platform. There are 3 steps you'll need to follow. First, you'll need to set up the software and tools needed to begin development. That means obtaining an account on ARM's Embed site and downloading the nexpaq application for the iPhone or Android, whichever you need. The tile, the application within an application that controls the module you'll develop, runs inside the nexpaq application. You write the tile code using a standard text editor and load it into the nexpaq application using iTunes if you're using an iOS device, or just drag and drop if you're using Android. Next, you'll need the hardware. That means getting 3 devices: a nexpaq development board, a Maxim MAX32625 development module, and a Maxim HDK board. We'll tell you where you can get these devices and how to use them. Finally, you'll plug everything together. There's a default application already loaded on the MAX32625 development module, and the nexpaq application has a default tile for this module already built in. You'll use the default tile to change the brightness and the color of the LED that's on the development module directly from your smartphone. Once we have everything working, we'll take a high-level look at what's actually going on there and look closely at the module firmware. But before we get bogged down in these details, you're going to need to set up the Embed developer account that we talked about. It's free, it doesn't require actually installing any software on your computer, and available anywhere you have an internet connection. Here's how to create a new account. Open a browser and navigate to developer.embed.org. On that page, you should see a Login Sign Up link. Click it and follow the instructions to create an account. Now to the nexpaq application. The nexpaq application runs on an iPhone or Android smartphone to manage the modules installed on any of nexpaq's phone cases and battery packs. When you plug, let's say, the button module into a nexpaq smartphone case, the case identifies the module and its capabilities. When the nexpaq application runs, it queries the smartphone case to find out which modules are installed and where. That's how it knows what tiles to display in the application. Now, when you're developing a new module, you write the HTML, JavaScript, and CSS code that describes how the tile looks and behaves, and the C++ code that comprises the firmware for the module. You load the firmware into the development module using Embed, but the code you wrote for the tile actually goes inside the nexpaq smartphone application. You load the tile code into your smartphone using iTunes for an iPhone. You add the code to the nexpaq application just like you would add media files to a player application. If you're using Android, it's a little simpler. Just drag and drop to the appropriate folder on the Android phone. To download the nexpaq application, go to nexpaq.com/app using the browser on your smartphone. There, you'll find a link for the iOS application and another link for the Android application. Just touch the link for the application you need. The application will be automatically downloaded to your phone. The last step in preparing to develop for the Maxim nexpaq Embed platform is to get the hardware. If you're attending a Maxim nexpaq event, you'll receive all the hardware you need at the event, except, of course, your development PC and a smartphone. You will need to provide these. But if you're not attending an event, the nexpaq development kit is available directly from nexpaq at www.nexpaq.com. The MAX32625 development module and the Maxim HDK board are both available from Maxim Integrated on their website, www.maximintegrated.com. To begin, let's start with the nexpaq development board. To set up the board, you need a USB power supply and a micro USB cable. Plug the micro USB cable into the USB connector closest to the module connector at the top of the board. When you have the board powered up, you'll see a blue LED light up in the lower right corner. That's it. Your dev board is ready to go. Now it's time to start up the nexpaq application on your smartphone. When you start up the application for the first time, you'll be invited to create an account. All users of the nexpaq platform create an account to keep track of their modules and to provide connectivity to the nexpaq web presence. Touch the Register button and fill in the requested information. When all the blanks are filled in, touch Create Account, and you're all set. Once you've created the user account, you'll be invited to connect to your nexpaq device. Now remember, the smartphone connects to the nexpaq gateway, not directly to any module, and when you're developing for the nexpaq application, the gateway is your dev board. So make sure your dev board's plugged in and powered up, and touch the button labeled Connect to My Device. Now if everything is working and you're in Bluetooth range, you'll see your nexpaq gateway listed on the Setup nexpaq page. The gateway will have a name consisting of 12 hex digits, the gateway's MAC address. Touch the gateway and then touch the Add nexpaq button. What happens next is that the smartphone attempts to connect to the dev board over the Bluetooth connection. If successful, you'll see a notification on your smartphone that the gateway is now connected. But what you see on the phone isn't going to be particularly interesting, just 6 blank tiles and a battery indication. We'll fix that soon enough. Now let's try our first module. Plug in the MAX32625 module into the module connector on the dev board. Be sure that the pins on the MAX32625 module face away from the center of the board. You should see the upper right tile turn a very pleasant teal with the label Max Dev Mod on it. Touch this tile. Now, if everything's working correctly, you'll see this. A somewhat stylized picture of the MAX32625 development board itself. Each pin is represented by an oval, and digital pins show a state indicator, bright green if the digital input is a 1, and dark green if the digital input is a 0. For the analog inputs, you'll see the actual voltages on each input. You have a 4-channel voltmeter here. In the middle of the image, there's a gray block with red, blue, and green values. These are the brightness values for the 3-color LED on the development module. The initial values are 0 for red, 178 for green, and 169 for blue. These colors combine to make that same pleasant teal that you've seen before. You can play with the values. Each of the red, blue, and green values can range from 0 to 255. When you change a value on the smartphone screen, you'll see the LED on the development board change color too. Each pin in the diagram has a combo box. You can make each pin an input with or without a pull-up or pull-down, or an output with an output value of 0 or 1. By default, each pin is configured as an input with a soft pull-up. Of the group of 4 pins at the bottom of the board just above the nexpaq module connector, the lower left pin is ground. You can connect a wire to that pin and touch it to any of the displayed pins that are configured as an input, and observe that the indicator turns off. So what's happening here really is pretty interesting. You can change the values for the LED on your smartphone and see them change the brightness of the LED on the development module. And you can ground a pin on the development module and see it reflected on the smartphone display. You have a kind of two-way communication. But how does it do that? Well, to explain that, it's best to take a high-level view. We'll get into the details later. Let's start with the module. There is code running on the module that is continuously listening for messages that come from the smartphone over Bluetooth. The radio is actually on the gateway and transfers data received from the smartphone over a SPI interface to the module. The listener is part of the nexpaq API. You don't need to worry about that code. In our application, the main loop runs once per second. When the main loop runs, it calls a routine that gathers information about all the pins on the device and transmits the status message via the gateway to the smartphone. When the smartphone receives the message, JavaScript code running in the nexpaq application parses the data and changes the state of the indicators on the smartphone screen. When the user changes a pin function by touching one of the pin combo boxes, the pin number and pin function are transmitted to the module through the gateway. The listener task gets the message and transfers the message to the code responsible for changing the pin function. That code parses the message and changes the function of the designated pin. Changing the LED color works similarly, but this time all three colors are transmitted at once. The listener receives the message and transfers the message data to module code that sets the LED color according to the red, green, and blue intensity values transmitted. The LED port is configured as 3 pulse-width modulated outputs, so you can continuously vary the brightness of each color from completely off to full brightness. Okay, that's the high-level overview. Next, we're about to drill down into the inner workings of the module firmware. There is a lot to see here, but it really will provide a lot of insight into how the nexpaq application platform actually works. But it might be a good time to grab another cup of coffee. This is the source code for the I/O demo module application. The first 2 lines of the program include the 2 platform libraries, embed.h and nexpaq.mdk.h. Including embed.h pulls in the entire Embed operating platform, and nexpaq.mdk.h adds nexpaq's module development kit framework. This lets you use quite a lot of complex functionality, but don't worry, ARM and nexpaq have made using the APIs pretty simple. The next set of lines are directed to the Embed operating system. They define Embed objects that manage each of the pins of the MAX32625. Now remember, C++ is an object-oriented language, and each Embed object defines both data elements, such as the output value, and methods, such as how to set the mode of the pin for each peripheral object. For example, the first line tells Embed to create an object, specifically a pulse-width modulated output that manages the pulse-width modulator attached to port 2, bit 4. It names the object LED-R. Each line in the block works this way. The types you see here, PWM-out, analog in, digital in-out, are object classes defined in the Embed OS. You can find the documentation for these and all other object classes in the Embed documentation that can be found on the Embed developer website at docs.embed.org. The next section you'll encounter is the definitions section. This is where we'll define any important constants that govern the operation of the module. In this program, we define 3 constants. The first, function table num, is the number of different messages from the smartphone we'll be listening for. In this system, we'll listen for just 2 different command message types, one that will configure the color of the LED, and another message type that will configure a pin. The second constant is UUID num. UUID stands for Universally Unique ID. Now, in this case, it really just defines the module type. For a development module, it's always 16. The third constant is the loop delay in milliseconds. In this case, we'll wait 1 second between loop cycles. Now we've configured all the pins for the device and covered the constants needed by the program, let's drop down to the bottom of the file and take a look at the main function. Every C program must have exactly one function named main. That's the function that takes control immediately after the system is reset. In an embedded system, the main function never returns. It simply loops until the system is reset or turned off. In our system, there are 3 functions that must be invoked before the system begins looping. The first, np API init, is part of the nexpaq API, and it initializes the nexpaq system and prepares it to begin communicating with the gateway. The next call is to app setup. This function is something that you write, and it initializes any peripherals and global variables that may need to be set up before the main loop starts running. The last call is np API start. This function kicks off the nexpaq API and lets it begin communicating with a smartphone application through the gateway. Now we come to the main loop. Within the while structure are three calls. The first, app loop, is the function that you write that contains everything you want to do within the loop. We'll look at that in just a moment. The next call is to a nexpaq API function, np API BSL check. This function checks to see if there is a request pending in the nexpaq bootloader. If there is, the function won't return. Usually the bootloader will do whatever is necessary, and then it will restart the system. The last function is part of the embed OS. Thread wait tells the operating system to suspend our task for the specified number of milliseconds. During that time, the OS can perform other functions like responding to messages from the smartphone. Now, do you see what's happening here? We're using resources from the nexpaq API, the Embed OS, and routines that we write to make the system behave the way we want. The nexpaq API manages the connection back to the smartphone. The Embed OS manages the resources on our microcontroller, and we write the initialization and the application loop. That's the main routine. Now, let's scroll up to the app setup function to see what it does. Well, except for one line, the app setup function looks pretty straightforward. The LEDR, LEDG, and LEDB objects were defined, remember, as PWM outputs. Each of these outputs are set to full-time on, floating point 1. All of the digital pins are configured the same way, input mode and a soft pull-up. And the communication buffer is filled with 1s. That's what the value hex FF does. Okay, that all makes sense. All the peripheral devices are initialized the way they should be. The buffer is initialized. But let's take a look at that one odd line. It uses a pretty normal C construct that puts a function call inside an if statement so that if the function call fails, we can take some remedial action. Inside the if statement, there's a call to a nexpaq API function, np API register. This function tells the nexpaq system what messages to listen for and what to do when it receives one of the messages. You do this by sending the function a pointer to a constant array. That array contains the message numbers to look out for and pointers to the functions that will handle each of those message types. You also send the API function the number of message types that you care about. In this case, the array is called myCommandFuncTable. And the number of message types we care about is 2. We saw that before when we set up the constant function table num. If we scroll up just a few lines, we can see the definition of myCommandFuncTable. You can see that it's defined as an array of exactly 2 elements. Each element is of the MDK register command type. MDK, by the way, stands for nexpaq's Module Development Kit. When you build this structure and pass it to the np API register function, what you're doing is registering a function to handle a particular command type. A structure of MDK register command requires 2 elements, an integer that contains the message type number, and a pointer to the function that can handle messages of that type. The 2 lines above the definition of myCommandFuncTable are the prototypes for the functions that will handle each of those message types. Now, what's happening here is we're setting up something called a callback. A callback is a function that we pass to the system to be called when some event occurs. Using callbacks instead of polling for the event reduces power, and it frees the CPU to do more important things. In our firmware, we register 2 functions that are called back when messages arrive from the smartphone. myFunctionCommand2700 and myFunctionCommand2702. They're named for the message numbers that are transmitted from the smartphone. Let's look at both of them. We'll start with a handler for message 2700. myFunctionCommand2700 is pretty straightforward. It takes the first 3 characters in the received data buffer and sends the values to the LEDR, LEDG, and LEDB PWM outputs respectively. The only slight kink is that the message contains an integer in the range from 0 to 255, and that has to be converted to a floating point value. But other than that, there's no mystery at all. That's how we were able to control the LED brightness. The last line of the function is a call to a nexpaq API function, np API upload. This is the function that is used to send a message to the smartphone, and in this case, it just confirms to the nexpaq system that we received the message and acted on it. The np API upload function takes three values: the message number, a pointer to the data buffer, and the length of the response. A message of type 2700 is acknowledged with a message of type 2701. Acknowledgements always have a message value 1 greater than the message they are acknowledging. The other message handler, myfunctionCommand 2702, is a little more complex, but only a little. The message for this command is only 2 bytes long, a pin index, and the pin mode value. Depending on the pin mode value, the pin will be configured as an input with or without pull-ups or pull-downs, or as an output, driving either a 0 or a 1 level. As before, the function ends by sending an acknowledgement to the nexpaq system using the np API upload function. Let's pause for just a moment and review what we've learned. First, your application must send an initialization message to the nexpaq system by calling the np API register function. That function takes a structure that tells the nexpaq system which messages are important and what functions to call when those messages are received. When you're notified that a message has arrived, you'll get a pointer to the data in the message and the length of the data, and you can do anything you want with that data. Just be sure to acknowledge to the nexpaq system that you received the message when you're done. There's just one more thing we need to take a look at: the apploop function. Now, remember, that's the part of the code that we write that contains what we want to do, in our application once per second, when the main program loop calls us. This part of the program looks a little complex, but when you break it down, it's really not too intimidating. The apploop function gathers the status of every pin and compiles the data into a character array called data_out. The data array is 10 bytes long. The first 8 bytes are the converted values of the 4 analog inputs, each converted sample occupying 16 bits. The last 2 bytes are the bit values of the 16 digital pins. Let's start with the first analog input. The AN0 object manages the first of the 4 analog inputs. It has a method, readU16, that returns the 16-bit converted voltage on analog input 0. But remember, the analog inputs on the MAX32625 are only 10-bit ADCs. The Embed system normalizes those inputs by shifting the value left by 6 bits. So, instead of returning a 16-bit value that ranges from 0 to hex 3FF, the readU16 method returns a 16-bit value that ranges from 0 to hex FFC0, unless, that is, the hardware detects an overflow condition. This can happen when the voltage on the ADC input exceeds its maximum allowed input value, and in that case, the Embed system returns a value of hex FFFF. That value signals the firmware that there's a problem, but what should the firmware do about it? Well, a very cool hardware feature of the MAX32625 is an internal voltage divider on each of the first 2 analog inputs, inputs 0 and 1. The voltage divider reduces the input value by a factor of 5 and presents the divided values for inputs 0 and 1 on ADC channels 4 and 5, respectively. Effectively, this gives the ADC system an overall resolution boost of about 2.5 bits. Now let's go back to our code. First, we read the value from input 0. If the value is less than hex FFFF, then the channel converted the input correctly and we can use it. But first, we divide the returned value by 5. We do this so that it will have the same scaling as the value read from the channel that has the voltage divider. We put the low order 8 bits in data element 0 and the high order 8 bits in data element 1. But what if the value we read is all ones, that is, hex FFFF? That means that the voltage on the input was too high to convert, and in that case, the firmware reads the value from the divided input, that is, AN4. We do the same thing for analog input 1. If it overflows, we read analog input 5 instead. The data values are packed into elements 2 and 3 of the data out array. The firmware reads analog inputs 2 and 3 and puts the converted values into the data out array. Analog input 2 goes into elements 4 and 5, and analog input 3 goes into elements 6 and 7. These analog inputs don't have voltage dividers. They don't need a check for overflow, but we still scale the converted values by 5 to keep the readings consistent with channels 0 and 1. The last step in the status report is to compile the 16 digital inputs into the 2 remaining bytes of the data out array. The digital pins are grouped into an array of digital in-out objects called digpin. Each element of digpin is itself a digital in-out object. One of the methods available to digital in-out objects is the read method. The read method returns the actual input value of the pin even if the pin is configured as an output. It always reflects the actual level that is on the pin. You get a value of 0 if the pin is low and a value of 1 if the pin is high. In our program, we read each pin and get either a 0 or a 1. Then we shift it into its assigned bit position and add the shifted values together to make the composite byte to be returned to the smartphone. So the value from digpin 0 goes into bit position 0, the value from digpin 1 goes into bit position 1, and so on, until we have all 8 bits. Those 8 bits go into element 8 of the data out array. And we do the same thing for digpin 8 through digpin 15, but those values go into element 9 of the data out array. Once the data out array is completely filled, the send status function is invoked to send the data to the smartphone. Send status just transmits the populated array up to the smartphone. Let's scroll up and take a look at it. The send status function is just a wrapper for a nexpaq API function we've seen before, the np API upload function. The only difference is that this invocation of the np API upload uses a different message number than we've seen before, message number 2800 hex. Now, this brings up something important. In the nexpaq API system, commands from the smartphone to the module are always even-numbered messages in the range 2700 hex to 27FE hex. Acknowledgements from the module back to the smartphone are always numbered exactly one more than the command. For example, a command numbered 2708 hex will be acknowledged with a message numbered 2709 hex. Unsolicited status updates from the module to the smartphone are always sent with a message number 2800 hex. Let's summarize then how you build the module code. Start your code file by including the Embed and nexpaq libraries. Using Embed objects, declare the peripherals you'll need for your project, and declare any global constants that you know you'll be needing. And now for each message type you expect to receive from the smartphone, write a function to deal with those messages. In our example, the commands received from the smartphone configured port pins or changed the LED settings. Your application will probably be different, but the overall structure will be the same. Create a constant array that contains the message IDs and a pointer to each of the functions that will be handling the incoming messages. And now you're ready to write the main function. Your main function starts by initializing the nexpaq API system, registering your callback functions with the nexpaq API system, and then starting the API. You'll also initialize any global variables and peripherals that you've set up. And now you're ready to enter your main loop. Call from time to time the nexpaq bootloader request function, and if you have any data to send to the smartphone, you can do that in the main loop as well. I know, there's a lot going on here, but the truth is that much of this code is a kind of boilerplate that really doesn't change much from one application to another. Most of the development task for the module is making project-specific changes to a file like this. You keep the pieces that don't change and change the pieces that define the core functionality of your project. So, that's how the default firmware in the module works. Now, in the next edition of this tutorial series, we'll build a complete application with the HTML tile code and the module code. See you then!